Good morning, and thank you for joining us today at the joint ASC meeting with Dallas and Fort Worth. My name is Andrea Taylor with the Fort Worth branch, and I'm here to introduce Dr. John Grounds, and he is presenting today on things they did not tell you about floodplains. Dr. John Grounds is Vice President and Director of Water Resources at LJA Engineering. John is a graduate of SMU and received his PhD from the University of Houston. John's 30-plus year career has focused on reducing our risk of flooding. He led the advancement of modern floodplain mapping with LIDAR and GIS during the Tropical Storm Allison Recovery Project. He has prepared hundreds of FEMA letter maps of change, multiple drainage master plans for cities, counties, and river basins, and has been an educator as an adjunct at Rice University and working with TWBD staff developing and teaching Floodplain Management 101. So thank you, Dr. Grounds, and we look forward to your presentation.
Great. Well, thank you, Andrea. This is going to be a rather eclectic mix of floodplain issues. And if you're involved as a community official, or if you're out there doing flood insurance study work or preparing drainage impact analysis, hopefully you've encountered these things. But if not, this will give you, again, a good chance to review some things that you may have never been told before. And the first of these is, what is a flood? Got a nice little background of a flood that occurred in May of 2020 of the Dallas area along the Trinity. But in general, a flood is a temporary condition, according to FEMA and their definition, where 2 or more acres of normally dry land are inundated, or 2 or more properties. So in order to have a flood, according to the Federal Emergency Management Agency, you need to have 2 or more acres and or 2 or more properties inundated by floodwater. And the National Flood Insurance Program, if you want to file an insurance claim, it has to involve surface water, and not only surface water, but that water has to accumulate on the surface before it enters the insured structure. So if you have groundwater coming through a foundation, that would not be considered a flood. And here's a couple of quick examples. We're going to play a game of flood or not flood. And on the top right, we have a picture of downtown Fort Worth with a pipeline break, a water main break in the city. And then below that, we have an above ground pool where the pool's collapsed and has flooded at least 1 backyard. So for a water main break, if that water accumulates on the surface and floods 2 or more structures, that would be considered a flood. And the same, if this above ground pool breaks and it floods 2 or more structures, that would also be considered a flood. But the insurance adjuster would probably come back to the homeowner and make a claim against the homeowner's insurance for the pool breaking. But let's say you have a French drain that clogs. So you have a below ground drainage structure and it clogs and it causes water to rise, but that water does not accumulate on the surface, but still enters the house through the slab, then that would not be considered a flood and you couldn't make a claim against flood insurance. And the different example, you do have accumulation of water on the surface, but it impacts only 1.5 acres and there's a single structure. So if it doesn't make 2 or inundate 2 acres or 2 structures, it wouldn't be considered a flood. And this person could not make a claim against their flood insurance. Okay, rainfall. Recently in the state of Texas, well, back in 2018, Atlas 14 was published. And here's a map on the right-hand side that shows the isohydrals for the 100-year 24-hour rainfall event for all of the state of Texas. And then the left-hand image is just a zoomed in area of the Gulf Coast area around Galveston Bay. And what's interesting, if you look at the changes from the old map to the new map, and consider that the original values were published by Technical Paper 40 back in 1961, there's been some differences. And those differences are kind of confined along the Interstate 10 corridor between Beaumont and Houston and Austin and Del Rio, but it also creeps down the Texas Gulf Coast towards Corpus Christi. And some areas of the state of Texas have had changes in the 100-year 24-hour rainfall event, which we use for design of detention pond systems and major conveyances through bridges and culverts, where it changed from 12 to 18 inches in the design storm. And if you look, the largest changes tend to be on the right-hand side, on the eastern side of the state towards Beaumont, in areas that were impacted by Hurricane Harvey. Well, how much of this had to do with Harvey? So Atlas 14 was published in draft that was quickly removed from the world, and they continued to do the analysis because they want to incorporate the extreme rainfall event that occurred during Hurricane Harvey. Well, after the review and some statistical analysis, Harvey was found to provide an additional 2 inches of rainfall when you compare it to the original version or from TP40. And what's pretty amazing about all that is Harvey was not a statistical outlier. But if you look at all the other factors that went into changing the rainfall in these Harvey impacted areas and the Gulf Coast, there is a longer period of record. We have 60 more years of rainfall. We have a denser rain gauge network. We have additional significant events that have occurred in the area. And if you look down at the bottom of the slide in the black, since 1960, again, when TP40 was published, there's been more than 100 different storms that have occurred. And with Tropical Storm Allison and the Tax Day flood, Memorial Day, Hurricane Harvey, and even Hurricane Carla back in 1961. So all these additional 100 plus events that have occurred have been picked up by additional rain gauges. We have better spatial coverage of the rain gauges, and then also improved methods for doing statistical analysis for determining what our 100-year rainfall events might be. One thing that's published within the documentation that's provided from Atlas 14, you think this would be a great opportunity to review our weather and see if there are some long-term changes within the climate. And within that document, they use a word called stationarity. It's the first time I've ever heard this word, but it just implies, or it just means that over a period of time that there's no significant change in these statistics. The mean, the standard deviation have all been consistent over time. There are no long-term trends. And this is going to be the one time that I'm going to read during the presentation, but a quotation from the Atlas 14 books are the current NOAA Atlas 14 frequency analysis methods assume stationarity in both the historical data used in making the estimates and in future conditions. We test the assumptions of stationarity by applying various statistical tests to the AMS, the meteorological data. So far, tests have shown very little observable or geographically consistent temporal change in these data. So the National Weather Service made the assumption that there weren't any changes, and then they went back and reanalyzed that and showed that there is no time-dependent changes, which is an indication that there's probably not climate change that has occurred within the past 60 years, or even prior to that, probably more than 80 years within the state of Texas. And they further go on to say that nonetheless, as mentioned, we continue investigation on this topic with our partners from academia. So they couldn't find climate change, but they turned it over to the academics to see if they can do some further studies and make a more consistent or a different determination about whether or not climate change has impacted our rainfall. Okay. So a question about flood insurance rate maps. If we have all these large changes in rainfall, doesn't that make our flood insurance rate maps obsolete? That's a question that we're answering here now across the state. And there are 2 counties that are already pretty aggressively reviewing that and updating their flood insurance rate maps to include Atlas 14 rainfall and better define our risk to flooding. So coastal issues. I know we're in North Texas, but we're all doing a lot of work for the Texas Water Development Board and the General Land Office right now that covers watersheds from the entire state, from the Panhandle all the way down to the coast. So some things you need to be aware of, and I'm going to take some time in reviewing all of this. This is a flood insurance rate map, and hopefully you can see there's some white lines across this flood insurance rate map. And those white lines are delineating different areas, different flood zones. And those flood zones are either zone VE zones, which are coastal zones where they're influenced by tides, on top of a storm surge, but there's also things called coastal AE zones, and those coastal AE zones are the same as the VE zones, except the wave heights within those are less than 3 feet. And what makes them different is how they are regulated. If you're in a VE zone, you're allowed to have the lowest horizontal structural member to be at or above the base flood elevation. But if you're in a coastal AE zone, that horizontal structural member is not considered, and you can just have the finished floor at or above the base flood elevation. So you can have a slab in a coastal AE zone. You need to have a structure elevated on piers in a coastal VE zone. And again, the only difference is how tall are the waves. They're both created by the storm surge. They're both created by wind action creating waves on those. I'm going to show you something. Here's Transect 68, for example. Those transects, you're starting in the water and you're walking landward. So you're going to pick up topography, you're going to pick up water surface elevations, and these are used for determining the wave heights. And here's an example. On the right-hand side, we have elevation, we got ground, so you're seeing where the topography leads us. And on top of that, the dashed line is the water surface elevation. And you can see that as you move landward, that water surface elevation actually decreases. And what's happening is that storm surge is dissipating the wave heights, that energy is being eaten up and the wave heights are less. So the water surface is decreasing. But if you look at the circled area on the right of this transect profile, it's published for the 0.2% or the 500-year event. So FEMA in the flood insurance study only publishes transect information in a profile for the 500-year event. You would think that same data would be available and published as part of the flood insurance study for the 100-year event, but that's not, true. And if you were to go and look at that transect and see what's published on this profile, they're typically truncated at the limit of a 100-year event. So these probably will continue, and this transect extends well beyond that 5,000 feet that's shown on the bottom, but they truncate the limit of where that 500 year is published based on the limit of the extent of the 100-year. And then introduce you something that's been fairly new over the past, 4 or 5 years, something called a limit of moderate wave action. So FEMA and their construction sciences division have continued to study impacts or damages on structures from waves. And what they found is that a wave height of 1.5 feet causes very significant structural damage. So on the regulatory side of things, when they change from a VE zone to a coastal AE zone, again, that differentiation happens at a wave height of 3 feet. Well, now they have significant data that says, hey, if the wave height is 1.5 feet, we need to let the public know about that. And the way they've done that is add this line, and it's a line that shows a little sawtooth kind of running around on this flood insurance rate map. So areas that are seaward of that have waves that are greater than 1.5 feet. Areas that are landward of that have waves that are less than 1.5 feet. So if a local community adopts this higher standard, then if you're seaward of that line, you would end up having to raise your lowest horizontal structural member at or above that LIMWA line at the base flood elevation that's published there in a coastal AE. A lot to take in, I know. All right, so floodways. Again, this is a section in Collin County of a flood insurance rate map where I actually did the studies for Pittman Creek and the tributaries back during the risk map days or the ramp days. And we'll talk a little about floodways. Hopefully you all have seen this image before, but the way that floodways are developed is after there's a nice calibrated hydraulic model. We've got a 100-year model created, and you'll take an artificial walls and you'll start to encroach on the areas outside of the channel center line. So we have floodway fringes that are outside of the floodway, and then we're squeezing the water between these two imaginary lines until there's a 1 foot increase, a surcharge within that area. And that's how we define the limits of our floodway. And you don't have to read all the text in here, just look at the larger all caps words in this thing. So FEMA allows, under the minimum standards, to place fill within the floodway fringe as long as it doesn't increase the water surface elevation by more than a foot. And I'm going to repeat that. You can place fill in a floodplain as long as it's outside of the floodway and have it increase that water surface elevation, and you would be in compliance with the National Flood Insurance Program. Now, once you touch the floodway, you have to then demonstrate that you have no rise. So if you're outside of the floodway and the floodway fringe, you can place all the fill you want. Once you touch that floodway, it is a mandatory requirement by the National Flood Insurance Program to develop a no rise certification to show that there's no increase. And another issue that I end up having to discuss with community officials fairly often is, when is a CLOMR, when is a conditional letter of map revision required? And there's really only two instances. One is if you touch the floodway and there's an increase larger than 0.00 feet in the base flood elevation, you have to do a CLOMR. Or if there is no floodway designated and you cause a 1 point or more than a 1.00 foot increase in the base flood elevation, you're required to do a CLOMR. So CLOMRs are not required except in these two very specific instances with the National Flood Insurance Program. So what are the problems with all of this stuff? What are the new things you need to learn from all of this stuff? Well, in doing the designation and doing the hydraulic modeling for a floodway, you're losing the storage in that floodway fringe area. So if you lose that storage, then you have increased peak discharges. If you have increased peak discharges in a smaller cross section, you're going to increase the water surface elevation. So for areas that have created a floodway with a 1.0 foot surcharge, in reality, since you've lost all that storage and you're not attenuating peaks anymore, you're going to have an increase in water surface elevation of greater than 1 foot. So not only does FEMA allow you to fill and to have an increase of more than 1 foot, the math, the modeling that goes behind that actually results in an increase of greater than 1 foot. So let's talk a little about the Texas Water Code. In the state of Texas, you are not allowed to divert water onto your neighbor. It's just that simple. And if you do divert water onto your neighbor, they are allowed to sue you for damages. So if I am a community that allows the minimum requirements from the National Flood Insurance Program, and fill is being placed in the floodway fringe, and it results in an increase in the water surface elevation and the flood happens, guess what? There's going to be a lawsuit, and a rightful lawsuit. So most communities have not just adopted the minimum standard. So looking at higher standards, thankfully for most areas, the standard of practice is that no fill is allowed in the floodplain unless you do a spoonful mitigation. If I put fill in the floodplain, I need to take fill out. And for any area within the floodplain, not just the floodway, most communities require the preparation of a no-rise certification. And then CLOMRs, oftentimes communities don't understand when they should require a conditional letter of map revision. And some communities just use this as a convenience. They may not have the staff with the technical capabilities of reviewing a flood insurance study model or a CLOMR. So they will have a developer or their engineer submit a conditional letter of map revision. That way it gets sent to FEMA, and FEMA will do a technical review on their behalf. Okay, limit a detailed study. So not everything's mapped. And there are 3 different conditions or ways that you can sit there and map a floodplain upstream of a limited detailed study. And again, a picture of Collin County where there are 2 of these 3 different ways of mapping, where on Panther Creek in the top, the study is in, you have a limited detailed study pointed out, And the area upstream of that is just mapped as a Zone X unshaded. So it's an area that's shown as being outside of the 500-year floodplain. And if you look at the bottom left at Cottonwood Branch, it's mapped as a Zone A. So it's still mapped as a 100-year floodplain. It's just that there are no base flood elevations that are associated with that Zone A, that 100-year floodplain. The third method is to do a Zone X shaded, which is an area that's within the 500-year. So what you need to consider is if you're ever doing any development, any work just upstream of a limited detailed study, the flood risks are really identical on either side of that line. And just because it may be mapped as being outside of the 500-year doesn't mean the flood risk is not the same as the portion of the stream downstream of that where they show a 100-year base flood elevation. Well, accuracy and precision. So I'm going to take you back to your high school days, probably either in math or your chemistry class, where you actually learned about significant digits. And again, a real quick review of that. When you're looking at significant digits, we remove leading zeros. So if somebody states that you have a slope of 0.003 feet per foot, that really only has one significant digit. And then you eliminate trailing zeros if they're merely just placeholders. So you wouldn't go to the store to buy 1.0000 apples. You're just going to buy one apple. So I have one apple, that's one significant digit. Or I could say that my house is 1.00 miles away, and that could be correct. That could be 3 significant digits if I'm able to measure that precisely and that accurately. And then eliminating spurious digits. If you report something to a greater precision than you're really allowed to measure. So if you go and look up what the volume of the Atlantic Ocean is, and then do a little bit of math, do some conversions, you might say that the Atlantic Ocean has a volume of 85,127,438.90234 cubic miles of volume. Well, that's a little excessive. That's being overly precise. And just because I can calculate a number with a computer or with a calculator doesn't mean I should represent my results that way. And oftentimes in the H&H world, we do that within our studies just to demonstrate that we can, have extra digits in our results and make them look better. Okay. So on to the inputs that we use for our hydrologic and hydraulic modeling. If you look at the variations for Manning's N for concrete pipe, you would think that would be universal and consistent across the state of Texas, and it is not. Whether in the North Central Texas Council of Governments with ISWIM or TxDOT, we have variations that a difference of 30% within these Manning's N's could result in a 70% difference in head loss. That's the difference that's going to be greater than 1/100th of a foot, which is the standard that we're held to in order to determine whether or not we have an impact. Again, Manning's N values are only to 2 significant digits. Expansion contraction coefficients very much the same. They're published. We're told what values are standard to use from the HECRAS manual. This table in this exhibit, there's 2 significant digits in there, but a lot of local criteria, you might only have 0.3 or 0.5 as the number to use. So you go anywhere from 2 significant digits to having only 1 significant digit. And I promise you, this is all going to be used in a point in a moment. And looking at Manning's N, Manning's N value, you can't have a different value every foot, or you can, but it just doesn't make any sense in modeling. So these parameters are lumped, and they're lumped grossly. And typically in a flood insurance study, they don't account for seasonal changes with vegetation or how often a channel is mowed or even the channel geomorphology. And if you look at a lot of the flood insurance studies that are currently published, many of them are based on data that's at least 20 years old, and some of them may be as old as 60 years old as far as what data was used in their original study that hasn't been updated in quite some time. So Manning's N again has 2 significant digits. And some other parameters that we include in our modeling is land use. Typically land use may be 1 or 2 significant digits. Often local criteria causes us to round these, our percent development numbers to the tens place, which means we can go and use the nomographs and tables that they published and have these nice round figures and easy things to look up. one significant digit. Our percent impervious values, again, are typically just 2 significant digits. We might have some that are 3. Rainfall, 3 digits, and then a basin development factor. So we're seeing the basin development factor hydrologic method starting to resurge. It was developed several, 20 years ago by the USGS as a quick and easy way of looking to see how development might impact the runoff from an area. And so the basin development factors are very simple whole number approximations that look at how an area is developed, what type of channelization, whether it's detention or whatever, but they're lumped parameters, and these are lumped into single digit numbers. So you may only have 1 or 2 significant digits from hydrology that's based in basin development factors. Okay. And again, topography, we have great, beautiful LIDAR these days, but if you look at LIDAR that has an accuracy, a vertical accuracy of 10 centimeters, that's only 0.33 feet. And so the vertical accuracy on its own for topography can violate our tolerance of showing an impact of 0.01 feet. So you take all of these things together and you say, okay, how am I going to determine the accuracy of my no-rise certification? So you're looking at the difference between the existing and proposed water surface elevations for typically a 100-year event. You're calculating this and presenting the data at 1/100th of a foot increment, but does the accuracy of these base flood elevations support the precision that you're getting from the study when the original accuracy of that flood insurance study is stated to be plus or minus half a foot? So we're looking at a 0.01 foot change, but the modeling that we're starting out with is plus or minus half a foot. And again, looking grossly at the base flood elevations within the Dallas area, base flood elevations will vary between 430 and 450 feet. And if you follow the rules that you learned in high school about significant digits, the base flood elevations, well, there's a little typo there, are really only 400 or 500 feet if you consider only one significant digit. So when you do your studies, again, I'm being facetious here, but when I'm doing my studies and I'm following the rules that we learned in high school for significant digits, I don't have an impact if my water surface elevation only changes by plus or minus 50 feet. I'd be happy if I could be limited to plus or minus half a foot, but that's still a very significant change in water surface elevation. Not acceptable. So if you look at the standard conventions and standards of practice and even consider calibration, we have to have a way of measuring the impacts from our studies. We have to have a yardstick to measure these things. So our engineering convention has adopted these standards of 1/100th of a foot over the, we have many decades of using this. And when we look at large scale things, the lump parameters like the Manning's N values tend to become more accurate because we're looking at, again, a gross view of what's happening in the watershed. We're not looking at it foot by foot. We're looking at the entire, 100 square miles or, 200 acres at a time. And then these inaccurate lump parameters, again, average out so we have better results that we can use for calibration and recreate observed events. Another good thing about these methods that we have standardized procedures on is they're easily reproducible from one engineer to the next, from one jurisdiction to the next. So we get consistent and standard procedures across different modelers, different engineering firms. But at the end of the day, it still violates the math and the chemistry and the scientific principles you learned back in high school. So a better explanation of all this. First, we don't need to consider looking at the elevation where we have 5 significant digits. Let's just look at the change in water surface. So if I look at the change in water surface, at most that change is going to be 3 significant digits. So we go from 5 and looking at elevations down to 3, and that seems a whole lot more reasonable in trying to match it up with the accuracy of our data. Well, the real reason we do this is it's federal law. It's in 44 CFR 60.3 that if I do a no-rise certification, I cannot cause a loss or an increase in water surface elevation greater than 0.00 feet. So that's where that 0.01 foot requirement comes from. And if we were allowed to have softer standards, then our modeling would tend to be less accurate because I could get away with having a 1/2 foot impact. And if I have a 1/2 foot impact and the engineer upstream of me has a 1/2 foot impact, the one downstream has a 1/2 foot impact, all of those will tend to accumulate. And at the end of the day, we're going to be aggravating flooding. So an overly precise standard keeps this from happening. So quick summary. Floods can be from other sources than rain. Atlas 14 and Hurricane Harvey have made flood insurance rate maps obsolete in some areas of Texas. The National Weather Service could not find long-term trends of increasing rainfall across the state of Texas. Coastal flood zones have more detailed published data for the 500-year than for the 100-year, but that data is often truncated. The limit of moderate wave action better defines areas subject to wave action that can cause damages, but this area is not yet regulated by FEMA. A floodway with a 1 foot surcharge will result in an increase greater than 1 foot. And the FEMA minimum criteria allows for water surfaces to rise from the placement of fill in the floodway fringe. Thankfully, we have state law and local regulations that keep us from just filling within the floodway and causing a rise and flooding our neighbors. And then upstream of the limited detailed study, there are 3 different ways of mapping that flood risk, but you should always consider adjacent to that limited detailed study that you're still probably within an unmapped 100-year floodplain. And then the overly precise standards for drainage impact analysis are not supported by what you learned in high school math, but are necessary to keep those water surface elevations from creeping up and increasing our risk of flooding. So with that, that's all I have for you today. If you have any questions or any comments, you can contact me at jgrounds@lja.com. I thank you for your time, and I hope you have a great day.
Thank you, Dr. Grounds. That was a great presentation, and thank you all for joining us today. Enjoy the rest of the presentations.